the definitions of Lewis acids and Lewis bases, and we'll also get into the definitions of Arrhenius acids and Bronsted-Lowry acids. And the other thing that we're going to do is we're also going to show how acids and bases react, and specifically the curved arrows or the arrow formalism behind how they react. And another key component that we'll be talking about throughout the entire portion of this show will be the pKa. Okay, so the idea with pKa is that pKa is equal to the negative log of the concentration of hydronium ions in solution, or H plus or H3O plus. It doesn't really matter because it's in water. So I'm just H plus, and then you have the conjugate base all over the acid. So the important thing to remember is that if you decrease to the lower the pKa, so actually a way to think about this would be if you have more conjugate base in the solution. So sorry, just to recap about like what an acid is and what a conjugate base is. So the idea is that when you have an acid, HA, all that happens is that when it's in water or whatever, it dissociates into H plus and an A minus, and A minus is basically is its conjugate base. So the conjugate base, so a real life application of this would be if you were to have HCl, and water dissociating into H plus Cl minus. So this would basically mean that Cl minus is the conjugate base of HCl. Okay, so that's just to sort of give you a recap of what what I mean by conjugate base and the acid and everything. Anyway, but the fact is pKa is very important, and it's the negative log of the concentration of all this. So if we have a high concentration of conjugate base, then that means that we will have a low pKa, because if this is high, then and this is in the numerator, this will give us a really big number, and then when we take the negative log of a big number, we get a smaller number. So that's why the pKa will decrease. Now, a fundamental question that I wanted to ask you is kind of, maybe why do you think that this is important? Well, this is important because whether an acid is strong or whether an acid is weak depends upon how stable its conjugate base is. So if there's a lot of conjugate base, the chances are that the acid had to be strong. Because whether an acid is, I think I already just said what I think I'm now being like a parrot, restating what I already said. But the idea is that the acid, the conjugate, is that if you have a strong just means propensity. So if it's a strong acid, it means that it has a high propensity to dissociate, which is why this will be higher. All right. So that's how that works. Okay. The stronger the acid, the more stable the conjugate base. So one thing I can do is I can say increase strength of acid. You increase the strength of the acid. You increase the amount of. Then that means that you will have more conjugate base, which means that you will have a lower pKa. Okay, so that's how it works. And there's a pretty good table of pKa's that you can look up. And in the video I'll have an attachment image of that pKa table because that'll really help you a lot, I think. So basically, all this aside, let's look at let's get into the nitty gritty. Let's look at some actual reactions going on. Okay, so let's look at let's see. Why don't we look at water? So we can look at water, which looks like this. Actually, let me think. So we have water, HOH plus HCl. Okay, so hopefully you can see that all right. You have water interacting with HCl. So So now the question is, which one is going to be the acid and which one is going to be the base? So it turns out that that the stronger it turns out that the stronger acid will end up being the acid, and the acid that isn't as strong will be the base. So specifically, we can look at pKa value. So the pKa of HCl is -5. And the pKa of water is about 16. It's specifically it's like 15.74, but we'll just say that. So sorry, this is this should be -5, and this is about 16, give or take. So what happens is to draw the arrow formalism. So we know that this is the acid. So the Arrhenius definition of an acid is that it makes H plus in solution. The Bronsted-Lowry definition is that it takes is that an acid donates an H to a base, and then the Lewis definition, which is really important. For organic chemistry, the Lewis definition just says that an acid is an electron acceptor. So bases tend to be things that have lone pairs, and because electrons that they can give up, also known as nucleophiles. So a nucleophile is something that has a lot of electrons. It's full of electrons, and it wants to give some of it up because it really wants a hydrogen to make another bond. So basically, of course, water is a weak weak nucleophile and whatnot. But either way, this is still gonna work out pretty smoothly. So the idea is that you always draw with these things. You always draw from the electron source to the electron sink. So the source of the electrons is going to be the lone pair. So I'm going to draw this like that. Okay. So I drew the lone pair going to here. All right. And so I drew the lone pair. So I drew the lone pair going to here. And then what I'm going to do is I'm going to draw this bond being broken, such that it'll look like this. So if you notice, what we'll get in the products is that we'll get Cl with a lone pair. Actually, it'll have 3 lone pairs, and then we'll have a hydronium ion. So those were the nuts and bolts of how this works.